Welcome. In this lecture I shall discuss air cycle refrigeration systems. So, the specific objectives of this lesson to discuss reverse Carnot cycle and its limitations, to discuss reverse Brayton cycle both ideal as well as actual, and discuss various aircraft refrigeration cycles, namely simple systems, a bootstrap system, a regenerative system, etc. At the end of this lesson you should be able to describe various air cycle refrigeration systems, state the assumptions made in the analysis of air cycle systems, show the cycles on TS diagrams, perform various cycle calculations, and state the significance of dry air rated temperature. Let me give a brief introduction. Air cycle refrigerant systems belong to the general class of gas cycle refrigerant systems in which a gas is used as the working fluid. So, here the working fluid is a gas, and this gas does not undergo any phase change during the cycle. That means, basically this cycle is all the processes in this cycle are essentially sensible heat transfer processes. There are no phase change processes, and applications of gas cycle refrigerant systems are in the areas of aircraft cabin cooling and liquefaction of various gases. In the particular this particular lecture, I will be confining myself to air cycle refrigerant systems. So, the liquefaction of various gases and all will not be discussed here. Before we take up the various cycles, I would like to mention here an important type of analysis known as air standard cycle analysis. Air cycle system analysis is simplified by making the following assumptions. The first assumption is that the working fluid is considered to be a fixed mass of air which behaves as an ideal gas. The cycle is assumed to be a closed loop cycle. All the internal processes are reversible, and the specific heat of air remains constant throughout the cycle. This particular analysis is what is known as cold air standard cycle analysis. You might have studied in thermodynamics, you might have used this particular analysis for analyzing gas power cycles. So, we will be using the same type of assumptions and same type of analysis for gas cycle refrigerant systems also. This analysis gives reasonably accurate results for almost all situations except for the process of throttling, because if you remember from the last lecture, the throttling cooling during throttling depends mainly on the real gas behavior. So, if you are assuming the gas to be ideal, then during the throttling there will not be any temperature reduction. So, as I said, these cold air standard cycle analysis is good for all the processes except the throttling. In the cycles that I am going to discuss in this particular lesson, we will not be encountering throttling process. So, this particular analysis is good for us at this juncture. Now, let us look at some basic concepts. How do we reduce the temperature of an ideal gas? We cannot reduce the temperature of an ideal gas by throttling, that is what we have seen in the last class. Then what are the other ways of reducing the temperature? You can reduce the temperature by making the gas to do work in an isentropic process, or by sensible heat exchange with a cooler environment. So, if the gas is doing work in an isentropic process, obviously its enthalpy or internal energy reduces. As a result, its temperature also reduces. The second way of reducing its temperature is by exchanging heat with a cooler medium. So, in the cycles that we are going to discuss in this particular lecture, we will be mainly relying on the isentropic process for reducing the temperature. When the gas does adiabatic work, its internal energy drops in a closed system and enthalpy drops in an open system. That means, whenever when the process is adiabatic, that means there is no heat supply to the system, nor heat supply from the system, and at the same time the system is doing work. Obviously, it will be doing work at the cost of its own energy. If it is in a closed system, then it will be its internal energy. If it is an open system, it will be enthalpy. So, it will be performing the work at the cost of its internal energy or enthalpy. Since it is delivering a net work output, obviously the internal energy or enthalpy have to reduce. Once these two are reducing, since we are assuming the working fluid to behave as an ideal gas, obviously the temperature has to reduce, because internal energy and enthalpy of ideal gases are functions of temperature only. So, temperature of the gas decreases during the process. So, you can see here for example, a closed system undergoing an isentropic process 1 to 2. So, the work output is given by m into u1 minus u2, which can be written as mCv into T1 minus T2, where m is the mass of the system undergoing the isentropic process, u1 and u2 are the specific internal energies at the beginning of the process and at the end of the process, T1 and T2 are the temperatures at the beginning and end of the process, and Cv is, as you know, is the specific heat at constant volume. So, since W is positive, U1 is greater than U2, so obviously T1 will be greater than T2. So, this is a typical equation for an isentropic process of a closed system. Of course, you can derive this very easily by applying the first law of thermodynamics to a closed system. Heat transfer rate is 0, so work transfer rate is equal to change in the internal energy. If you apply the same first law of thermodynamics to an open system, then you get the equation in the form W is m dot into H1 minus H2, which can be written as m dot Cp into T1 minus T2, where W is the power output, m dot is the mass flow rate of the working fluid, H1 and H2 are the initial and final enthalpies, T1 and T2 are the initial and final temperatures, and Cp is the specific heat at constant pressure. And for both closed as well as open systems, you can very easily show that whenever an ideal gas is undergoing isentropic expansion, the temperature is related to pressure. That is given by this relation shown here, T2 is equal to T1 into P2 by P1 to the power of gamma minus 1 by gamma, where gamma, as you know, is equal to Cp by Cv for ideal gases. This equation can be very easily derived by applying two equations. One is ideal gas equation of state, that is PV is equal to RT, and the second is the process equation for an isentropic process, that is PV to the power of gamma is constant. So, if you are using the equation PV is equal to RT and also PV to the power of gamma is equal to constant, then you can get this expression for the temperatures in terms of the pressure ratios. Now, let us begin our discussion with an ideal cycle called a reverse Carnot cycle for gases. This is an ideal cycle for constant temperature, heat source and sink. That means, whenever we have an external heat source or sink which is at a constant temperature, then the reverse Carnot cycle is the ideal cycle. So, it is a completely reversible cycle. So, let me describe this cycle now. Yeah. So, this cycle consists of 4 processes. First process, process 1 to 2 is isentropic compression, process 2 to 3 is isothermal compression, process 3 to 4 is isentropic expansion, 4 to 1 is isothermal expansion. So, this can be achieved either by using a closed system concept or an open system concept. For example, you can have isentropic compression, expansion, etc. using a piston cylinder device, in which case the system becomes a closed system. Or you can also have an open system where there is a steady flow of the working fluid through each component. So, what the example I have shown here is for an open system. So, typically steady flow energy equations can be applied to each of the components. Okay. So, the first process, process 1 to 2. This is, as I said, is an isentropic compression. This is achieved in a compressor which compresses the working fluid from point 1 to point 2 in an isentropic manner. In fact, it is an irreversible, I should mention that it should be reversible adiabatic compression process, which turns out to be an isentropic process. So, for this process you have to supply some work input. Okay. Let that work input be W1 to 2, okay, and there is no heat transfer because this is an adiabatic process. Okay. So, W12 is the work transfer during this process. This is the work input to the compressor. Next, what happens is the gas, which is now at a high temperature and high pressure, undergoes what is known as an isothermal compression. Okay. You can see that process 2 to 3 is an isothermal compression. That means its temperature remains constant during the process, at the same time its pressure increases. Okay. This is a compression process. So, you have to supply work input to the compressor. Since its temperature has to remain constant, obviously there must be some heat transfer, and if you are applying steady flow energy equation, you can easily show that the work input should be same as the heat transfer rate, so that your temperature remains constant for the ideal gas. Okay. And process 3 to 4 that is taking place in an isentropic turbine. So, during this process it gives out actually a work output. Okay. So, this is the work output from the turbine, and this is, as I said, is an isentropic process. So, during this process its pressure and temperature and enthalpy, everything reduces. So, the enthalpy, temperature and pressure at point 4 will be lower than at point 3. Okay, and actually what is done here, you can see that the turbine and compressor are coupled here. That means the work output of the turbine is supplied to the compressor. Okay, so the net work output here will be W12 minus W34. Okay. The next process is what is known as isothermal expansion, process 4 to 1. This takes place in an isothermal turbine. Its temperature has to remain constant. At the same time, it has to extract heat from a low temperature reservoir. That means here it will be rejecting heat to a high temperature heat sink, and it will be extracting heat from a high temperature heat reservoir or heat source. Okay. Since its temperature has to remain constant, that means obviously this process will take place only when some work is done, and this QL will be same as equal to WL. Okay. And this is the useful refrigeration effect, useful cooling effect. So we have two compressors and two turbines. One compressor is an isentropic compressor, one compressor is an isothermal compressor, one turbine is isentropic turbine, the other one is isothermal turbine. Let me show this cycle on TS and PV diagrams. Okay, so here you can see the TS and PV diagrams here. You can see that this is the two-phase region. Okay, since this is a gas cycle, the complete cycle will be taking place away from the two-phase region. So you don't really have any liquid phase. Okay, and the four processes described earlier, process 1 to 2, isentropic compression. You can see that the x-axis is entropy and y-axis is temperature. So isentropic compression means it will be a vertical line from a low pressure P1 to an intermediate pressure P2. Okay, so this is a vertical line, and the process 2-3 is isothermal compression. Okay, so pressure increases again from P2 to P3. At the same time, the temperature remains constant, and during this process, this much amount of heat is transferred. Okay, and process 3 to 4 is isentropic expansion in the turbine. Entropy remains constant, temperature falls, and process 4 to 1 is isothermal expansion. So you have to supply heat Q4 to 1, which is the refrigeration effect here, and the same process is shown here on PV diagram. Okay, so 1 to 2 is isentropic process, 2 to 3 is isothermal, 3 to 4 is again isentropic, and 4 to 1 is again isothermal process. And by applying our TdS relations and first and second law equations, you can show that the heat transfer during the process Q2 to 3 is integral TdS from 2 to 3, and temperature remains constant. Let this temperature be Th. Okay, then Q2 to 3 is nothing but integral TdS, which is equal to Th into S2 minus S3. Similarly, heat transfer during the process 4 to 1 is integral TdS from 4 to 1, which is equal to TL S1 minus S4, where TL is the low temperature. So basically the Carnot cycle operates between two temperatures, one is the low temperature and the other one is the high temperature, and this is the heat transfer during the heat rejection process and heat transfer during the heat extraction process. And now if you apply the first law of thermodynamics to the entire cycle, so as you know, first law is nothing but cyclic integral of dou Q should be equal to cyclic integral of dou W. Okay, so what is the different heat transfer rates to heat transfers during the cycle? We have heat transfer taking place only during two processes, process 2 to 3 and process 4 to 1, and Q41 is positive because you are supplying heat to the cycle, and Q2 to 3 is negative because heat is being rejected from the cycle. So we are following the sign convention. So cyclic integral of dou Q is equal to Q4 to 1 minus Q2 to 3, and cyclic integral of dou W is nothing but net work input to the system. Okay, and then the COP of the system is defined as the cooling effect divided by the net work input, that is Q4 to 1 divided by W net. Okay, so if you are substituting these expressions here, you will ultimately find that COP of the Carnot cycle is simply equal to TL divided by TH minus TL. That means it is only a function of TL and TH. Okay, so it is independent of your working fluid and all that. This is one very peculiar this thing of Carnot cycle. It is only a function of temperatures. Okay, and from the expression you can see that COP increases as TL increases, and COP also increases as TH reduces. So basically the COP of a Carnot system increases as the temperature difference between the high temperature and low temperature reduces. Okay. So we have seen that the COP is a function of high and low temperatures only, And what are the limitations of, as I said, this is an ideal cycle. So, normally Carnot cycle cannot be built in practice, but this is used as a reference. So, normally we use it as a standard and we compare the actual cycles with the Carnot cycles just to know how good is our cycle compared to the best possible cycle. Okay. So, the best possible or the ideal cycle is most of the cases Carnot cycle. Okay. But as I said, Carnot cycle is not possible in practice. Especially Carnot gas cycle is not possible in practice because of the limitations. What are the limitations? The first limitation is that the isothermal compression and expansion are difficult to achieve in practice. So, you have seen that process 2 to 3 and process 4 to 1 are isothermal processes, at the same time some work transfer has to take place. Okay, so this is very difficult to achieve, especially when we are dealing with high speed turbines or high speed compressors. They will be operating closer to adiabatic conditions than isothermal conditions. So, achieving the isothermal compression and isothermal expansion is very difficult. So, normally it is not possible in practice. So, this is the first limitation. The second limitation is that Carnot gas cycle offers very small volumetric refrigeration capacity. As a result, the amount of air that has to be handled by the system will be very, very large. So, this is another practical limitation. So, you really do not find any reverse Carnot cycle working in practice. So, now let us look at a cycle which actually found in practice, okay, which can be built. Okay, this is high volumetric flow rates. So, such a cycle is known as reverse Brayton cycle. Let us first look at ideal reverse Brayton cycle. This is actually a modification of Carnot cycle, and this is also known as Bell-Coleman cycle or sometimes as Joule cycle. Okay, so Bell-Coleman cycle, reverse Brayton cycle and Joule cycle mean the same thing. And this is widely used in aircraft refrigeration, and this cycle is internally reversible. Carnot cycle is both internally as well as externally reversible. So, you call Carnot cycle as a completely reversible cycle. That means the heat transfer rate, for example, you take a heat transfer process in a Carnot cycle, it has to be internally reversible and it has to be externally reversible. That means heat transfer between the external source or sink and the working fluid must take place reversibly. That means there should not be any temperature difference between the source or sink and the working fluid. Okay, then you call it, and there are no internal irreversibilities also. Such cycles you call as completely reversible cycle. The Brayton cycle that we are going to discuss now, they have to be internally reversible. That means there should not be any internal irreversibilities such as friction, fluid friction, etc. Let me show the cycle now. Okay, so what I am showing here is a schematic of the cycle. So, it consists of 4 components. One is a compressor, a high temperature heat exchanger, a turbine and a low temperature heat exchanger. Okay. So, if you see the compare this cycle with Carnot cycle, you will find that there are 2 changes. The first change is that the isothermal compression here is replaced by a heat exchanger. That means isothermal compressor is replaced by a heat exchanger. Similarly, the isothermal turbine is replaced by a low temperature heat exchanger. Okay. Now, what are the 4 processes in this particular cycle? The first process 1 to 2 is isentropic compression. Okay. So, the air or working fluid gets compressed isentropically in the compressor. So, it is isentropic compression, and process 2 to 3 is isobaric heat rejection. This was isothermal heat rejection in case of Carnot cycle, but in the isothermal process is replaced by isobaric process in Brayton cycle. Okay, so process 2 to 3 is isobaric heat rejection. Then process 3 to 4 is isentropic expansion, and process 4 to 1 is isobaric heat extraction. So, the only changes are in the process 2 to 3 and 4 to 1. Process 1 to 2 and 3 to 4 are same as Carnot cycle. Okay, so this is the simple reverse Brayton cycle. Now, let me show this cycle on TS diagram. Before I show this cycle, let me once again point it out that here we have clubbed the shaft of the turbine is connected to the shaft of the compressor. That means the work output of the compressor turbine is supplied to the compressor. Okay. So, still this cycle requires some positive net work input to the system. Okay. You can never have the work output of the turbine greater than the work input required for the compressor, because that will violate the second law. Okay. So, there must be always some net work input to the system. Okay. So, that net work input is the difference between the work of the compressor minus the work of the turbine. Okay. So, now the process is shown on TS diagram. As you can easily see that you have two pressures here. Let us say that this is pH or okay, P2 and this is P1, and this P is constant. So, P2 is equal to P3 and this is again an isobar. So, P1 is equal to P4, okay, and P2 is greater than obviously P1, right. So, process 1 to 2 is isentropic compression. So, it is a vertical line. Process 2 to 3 is isobaric heat rejection, that means along the constant pressure line, and during this process you can see that the temperature of the air drops from T2 to T3, and process 3 to 4 is isentropic expansion in the turbine, okay. So, it is again a vertical line, and process 4 to 1 is again isobaric heat extraction from the heat source. That means basically you have heat extraction from the low temperature heat source and heat rejection at this point, okay. And as you know, if you are using it for cooling, this is our required cooling output, okay. Now, we can quickly write the equations for various processes. For example, process 1 to 2, what we are doing is we are simply applying the steady flow energy equation. We are neglecting changes in kinetic and potential energies, okay. So, these are the two assumptions. Apart from that, we are following the cold air standard cycle analysis, okay, that you must keep in mind always for this lecture, okay. So, for process 1 to 2 is isentropic compression. So, there is no heat transfer, only work transfer takes place. So, this is the work input to the compressor. This is simply equal to mass flow rate of the air into H2 minus H1. This is enthalpy change during the compression process, okay. So, m dot into H2 minus H1. So, H2 minus H1 is written as Cp into T2 minus T1, where Cp is the specific heat, T2 and T1 are the final and initial temperatures for the compressor, okay. And process 2 to 3, if you remember, is isobaric heat rejection, okay. During this process there is no work done, that means there is no work transfer during this process, okay. So, W23 is 0 because this process was performed in a heat exchanger, so no work was done. So, when this is 0 and when again delta Ke and delta Pe are negligible, if you are applying steady flow energy equation, you can easily show that Q2 to 3 is m dot into H2 minus H3, which is equal to m dot Cp into T2 minus T3. And process 3 to 4 is isentropic expansion. So, Q dot 3 to 4 is 0, okay. So, W 3 to 4 is Q m dot into H3 minus H4, which is equal to m dot Cp into T3 minus T4, and finally process 4 to 1, again work is 0 during this process and it is isobaric heat rejection. So, you can write this as m dot into H1 minus H4, which is equal to m dot Cp into T1 minus T4. Again for the process 1 to 2, you can get this equation very easily, as I was mentioning in the little while ago. You can get this expression. How do you get it? We can write PV is RT and P1 V1 to the power of gamma is P2 V2 to the power of gamma, okay. So, if you are using these two equations, you can arrive at this expression, okay. So, what it shows is the exit temperature of the compressor is equal to the inlet temperature multiplied by the pressure ratio to the power of gamma minus 1 by gamma, where gamma is, as you know, is Cp by Cv, okay. I am writing this as T1 into Rp to the power of gamma minus 1 by gamma, where Rp is equal to P2 by P1. So, this is called as pressure ratio. We have only two pressures in this cycle, so this is the pressure ratio, okay. Similar to the process 1 to 2, process 3 to 4. Process 3 to 4 is isentropic expansion. So, again you can get this equation for the process 3 to 4, where T3 is equal to T4 into P3 by P4 to the power of gamma minus 1 by gamma, which is again equal to T4 into pressure ratio to the power of gamma minus 1 by gamma, okay. So, from these two relations you can very easily show that T2 by T1 is equal to T3 by T4, okay. And now we apply the first law of thermodynamics for the entire cycle. So, as you know, cyclic integral of del Q is equal to cyclic integral of del W, and heat transfer took place in two processes, 4 to 1 and 2 to 3, and this is positive because it is taking heat from the heat source. So, for Q4 to 1 is positive, it is rejecting heat. So, Q2 to 3 is negative, okay. And there are two work transfer processes, process 3 to 4, that is the isentropic expansion in the turbine. It is positive because system is doing the work, and this is the work input to the compressor. It is negative because you are supplying the work to the system, okay. and this thing is equal to W net, right. So finally you find the W net is equal to Q4 minus Q4 to 1 minus Q2 to 3. So COP again we are defining as Q4 to 1 divided by W net. So you can very easily show that this is equal to T1 minus T4 divided by T2 minus T1 minus T3 minus T4, and this we can easily show, because as I said you can write this expression T2 by T1 we have just now shown is equal to T3 by T4. So if you are using this expression here, you can arrive at this equation, okay. And you can also write COP in terms of pressure ratios, okay. So again the relation, you remember the relation I have shown just now. So ultimately you can express COP in terms of pressure ratios and gamma, okay. So finally the COP of the ideal reverse Brayton cycle becomes a function of the pressure ratio, and it is very easy to show that COP reduces as pressure ratio increases, okay. That means higher the pressure ratio, smaller will be the COP, okay. So these are the typical equations, and it is very easy to derive these equations on your own. All that you have to do is take each component and apply steady flow energy equation to the component, okay, and assume the Cp to be constant, neglect kinetic and potential energy changes, and apply steady, as I said, steady flow energy equation to all the components, okay. Right. So we have seen that this is, I have already mentioned, the two isothermal heat transfer processes are replaced by two isobaric heat transfer processes, and for the same heat exchanger terminal temperatures you can very easily show that the COP of a reverse Carnot cycle is always greater than the COP of a Brayton cycle, okay. Let me show this. Okay. Right, I will show this a blank sheet. Okay. So what I am showing here is the reverse Brayton cycle 1, 2, 3, 4, right. So you have two isobaric processes here, okay. Process 2 to 3 and 4 to 1 are isobaric processes, process 1 to 2 and 3 4 are isentropic processes, okay. And if I am fixing the terminal temperature of hot and cold heat exchanger, that means if I am fixing temperature at point 1 and temperature at point 3, then 1, 2 dash, 3, 4 dash will be a Carnot cycle which has the same terminal heat exchanger temperature as that of a reverse Brayton cycle, okay, right. So now for the reverse Brayton cycle, just now we have shown that the efficiency is given by T4 divided by T3 minus T4, that means this temperature divided by this temperature minus this temperature, okay. What is the COP of the Carnot cycle? COP of the Carnot cycle is obviously depending upon these two temperatures, okay, TH and TL. Here TH and TL are nothing but T3 and T1. So Carnot cycle COP is given by T1 divided by T3 minus T1, okay. So this will always be lower than this. Why? Because T4 is always lower than T1, okay. T4 is always less than T1. As a result, COP of the Brayton cycle will always be less than the COP of a reverse Carnot cycle, okay. Now let us look at actual reverse Brayton cycle. Whatever we have been discussing so far is an ideal cycle. So the actual cycle differs from ideal cycle due to two reasons. The first reason is the non-isentropic compression and expansion processes. That means basically the process 1 to 2 and 3 to 4 could be adiabatic, but they will be definitely irreversible. That means there will be some irreversibility maybe due to fluid friction, okay. So the process becomes non-isentropic. This is the first difference between the ideal cycle and the actual cycle. And the second difference is we have neglected all the pressure drops in the cold and hot heat exchangers. Typically when a fluid flows through a heat exchanger consisting of long lengths of tubes, there will be fluid friction and pressure drops, okay. In the ideal cycle we consider that there are no pressure drops, so you have only two pressures, whereas in actual cycle there will be pressure drops, right. So these are the two reasons why actual cycle differs from an ideal cycle. I can show this thing on a. So you can see the difference here. Here 1, 2, 3, 4. 1, 2, 3, 4 is the ideal cycle. Okay, and 1, 2 dash 3, 4 dash. This is 0.4 dash. Okay, so 1, 2 dash 3, 4 dash is the actual cycle. Okay, so you can see that, for example, process 1 to 2 in the ideal cycle it is an isentropic process. Okay, in the actual cycle it is non-isentropic. Okay, that means entropy increases during the process because of the irreversibilities. That means you will find that entropy at point 2 S2 dash will be greater than S1, whereas S2 is equal to S1. Okay, so this is one difference. So what is the consequence of this difference? You will find that temperature T2 dash will be larger than temperature T2. Okay, because of the irreversibility, you find that exit temperature is higher compared to the ideal isentropic process. Okay, and process 2 to 3. In actual this should have been point 2 should have been here. Okay, and the heat rejection should have taken place ideally along a constant pressure line, but you will find that because of fluid friction there is a pressure drop here. Okay, so you find that there is a reduction in pressure during the heat rejection process. Similarly, process 3 to 4, entropy remains constant if it is an ideal process, but in an actual process again entropy increases. So S4 dash will be greater than S3. Okay, so the process is something like this. So as a result, you have a cycle 1, 2 dash, 3 dash, 4 dash in an actual case. What is the consequence of this? You can very easily show that the consequence of this is a reduction in the COP. Okay, the COP reduces because of two reasons. First reason is that your cooling effect is reduced, because in an isentropic process, isentropic expansion process, the temperature should have been 4, but because of the irreversibility now the temperature is 4 dash. Okay, so T4 dash is greater than T4. Okay, and your useful refrigeration effect QL is m dot Cp into T1 minus T4 dash in case of an actual cycle, right, and in case of an ideal cycle this will be T1 minus T4. Since T4 is lower than T4 dash, obviously QL in actual case will be smaller. Okay, and we can also define the actual work of compression and actual work of turbine by defining isentropic efficiencies. Okay, for example, the actual work input to the compressor during the process 1 to 2 is defined as the isentropic work divided by the isentropic efficiency. Okay, so you can see that typically this isentropic efficiency of the compressor will always be less than 1. That means W12 actual will always be greater than W122 isentropic. Okay, so the required work input increases because of the irreversibility, right? And the next process, that is isentropic expansion in the turbine. The work output of the turbine now gets reduced because of the inefficiency. Okay, and here again we define an isentropic efficiency for the turbine. Okay, again this is lower than 1, so the work output of the turbine will be lower than the work output of the ideal turbine. Okay, so the net result is that W net in an actual case will be much larger than W net of ideal case, because output is reducing and input is increasing. Okay, and you can easily write the isentropic efficiency for the compressor in terms of the enthalpies. Okay, let's look at the earlier diagram. So it is defined as the actual and the enthalpy change divided by the enthalpy change for an isentropic process. Okay, and this can be written in terms of temperatures because we are assuming the Cp to be constant. So isentropic efficiency of the compressor is written as T2 minus T1 divided by T2 dash minus T1, and if you remember T2 was greater than T2 dash. Okay, so obviously this isentropic efficiency will be I'm sorry, I think it is the other this thing other way. T2 is actually lower because T2 dash is for the isentropic process. Okay, so this will be greater than 1, right? And for the turbine also you can write the efficiency in terms of the temperatures. Okay, again this will be less than 1, okay, because as you have seen the actual temperature at the exit of the turbine will be higher than the temperature in an isentropic process, okay. So, as a result, as I said just now, the net work input increases. Right. So, we find that COP of actual reverse Brayton cycles will be considerably lower than the ideal cycle because of these two effects, reduction in the cooling output and increase in the net work input. In fact, the reduction could be quite considerable depending upon the design, and one way of improving the system performance is to design efficient compressors and turbines. Actually, this is a very critical issue, okay. So, if you want to have a good efficiency, you must have efficient compressors and turbines. Now, Brayton cycles can be open or closed, okay. So far we have discussed a closed cycle, okay, that means the same amount of air is flowing through the cycle repeatedly, but in actual case you can have a open cycle or a closed cycle. So, let us see what is an open cycle. In open systems, cold air at the exit of the turbine flows into the cold space and cold heat exchanger does not exist. That means what we do in an open system is air from the turbine is directly released into the cold space. For example, if you are using it for an aircraft cooling, you directly release the cold air into the cabin of the aircraft, okay. So, the air gets heated up as it picks the heat from the cabin, okay, and then you take the air and send it to the compressor, okay. So, you really do not have a low temperature heat exchanger, okay. So, this is an open system, right, and there is no guarantee that the same air is flowing through the compressor, okay. The advantage of this system is obviously its simplicity, and since you do not have a cold heat exchanger, the total weight of the system will be reduced considerably, okay. That is the reason why we use this in aircraft cooling, okay. And second characteristic is typically the low side pressure will be atmospheric. When you are releasing the air into an occupied space, typically occupied space pressure should be close to the atmospheric. So, the low side pressure also has to be close to the atmospheric, okay. So, these are the two characteristics of open systems. As against this open system, in a closed system we have two heat exchangers, the high temperature heat exchanger and a low temperature heat exchanger, and the air of the system does not get mixed with the outside air. That means the same air flows through the cycle repeatedly. And one advantage of this system is that you can have low side pressure higher than the atmospheric, okay. Such a cycle is known as dense air system. That means you can operate your low side pressure at pressures much higher than the atmospheric, typically 3 to 4 bar, okay. That means the air will be quite dense, okay. So, you call these systems as dense air cycles. What is the advantage of dense air cycles? As you know, as you are increasing the pressure, the density increases, specific volume reduces, and for the same mass flow rate, the amount of volume that you have to handle will be reduced considerably, okay. So, that means volumetric flow rate of air reduces considerably. So, this will give you a lot of savings in terms of heat exchanger sizes, compressor sizes, etc. Okay. So, this is the advantage of dense air cycles, okay. So, dense air cycles are obviously possible only with closed cycle systems, and you can also use gases other than air. For example, if you have a closed cycle system, it is not necessary that you have to use air only, okay. You can also use other gases such as helium or any other gas, okay. Such systems exist for other applications other than aircraft cooling, okay. Typically in aircraft cooling we use air, so and normally it will be open, okay. Now let us look at aircraft cooling systems. So, why do we need first of all air conditioning or cooling in an aircraft? We know that as you go up, typically aircraft will be flowing at very high altitudes. It could be as high as let us say 10 kilometers or even more. So, as you know that as you go up, the temperature and pressure both reduce. In fact, at an altitude of 10 kilometers, the outside temperature can be as low as minus 30 or minus 40 degrees centigrade, okay. When the outside temperature is so low, why do you need a cooling system? Maybe you may be thinking that you require a heating system, because outside temperature is very low and the required comfort temperature is about 21 degrees or so, right. So, there is a large temperature difference between the inside and outside, okay. So, if at all there is any heat transfer, it should take place from the inside to the outside. That means you require a heating system, not a cooling system. But you find that in actual practice we need a cooling system, not a heating system, when the aircraft is flying at high altitudes. This is because of the following reasons, okay. The first reason is that there will be large internal heat generation. Okay. So, typically in an aircraft there will be a lot of heat generation because of the occupants. So, normally they are very compact, so a lot of occupants will be there in the population density will be very high in a typical aircraft, and everybody will be releasing heat, okay, due to metabolic rate and all. So, there is large heat generation in a small volume, right. So, this will add to the sensible and latent heats of the system. Okay. So, as a result temperature and moisture content will increase. Apart from the occupants, you can also have in fact you will also have a large amount of equipment which will be releasing heat, okay, many electronic controls, motors, etc. Okay, all these equipment will be releasing heat continuously. So, you have continuous heat addition to the air inside the cabin because of the people and equipment. Okay. So, if you and this will not this will be much more compared to the heat transfer from the cabin to the outside. Okay. So, if you do not provide any cooling system, because the internal heat generation temperature can shoot up. This is not the only reason, you also require cooling because there will be heat generation due to skin friction. Typically aircraft will be moving at very high speed. Okay. So, when it is moving at very high speed in an air, there will be large relative velocity. Okay. So, the boundary layers will develop on the surface. Okay. And since air has a finite viscosity, as you have seen in the earlier classes, there will be frictional losses, and because of the skin friction temperature rises. Okay. The temperature of the body, outside body, will be higher because of the skin friction. So, there will be actually heat transfer from the surface of the body to the interior because of the skin friction. Okay. So, this is the second reason why you need a cooling system. The third reason is the ram effect. So, because of the ram effect also the temperature of the air increases. Okay. So, I will explain the ram effect in a little while. And the fourth effect is solar radiation. For example, if the aircraft is flying during the daytime, then there can be considerable solar radiation, and because of solar radiation the temperature can go up. So, these are the four reasons why we need a cooling system. Okay. Typically, if the aircraft is flying at low altitudes, at low velocities, then maybe you can do away with the air conditioning system, but if it is flying at high speeds and at high altitudes, an air conditioning system is a must. Now, air cycle refrigerant systems are preferred in aircraft. So, why do we use air cycle refrigerant systems in aircraft? Because of the following reasons. The first reason is that obvious reason, air is cheap, non-toxic and non-flammable. Okay. Typically, you do not want to use any explosive or flammable gas in an aircraft. Okay. It has to be absolutely safe. So, air is the safest refrigerant that you can think of. It is easily available, it is non-toxic and non-flammable. Okay. So, this is one of the main reasons why we use air in aircraft refrigeration. Okay. The second reason is the leakage of air is not a problem. So, leakage of air from the system is not a big problem. And an open system can be employed eliminating cold heat exchangers. As I was mentioning just now, if you are using air, you can have an open system. That means you can directly release the air into the system. You need not have a cold heat exchanger. What is the advantage of not having a cold heat exchanger? As I have mentioned, the system weight will be reduced considerably. When you are designing an air conditioning system for aircraft, the most important criteria is the weight per kilowatt. Okay. So, the weight is a very important factor, and the volume is also of course an important factor. The system that you choose must be lighter. Okay. So, you will see that for aircraft air conditioning, the air cycle systems will be lighter. Okay. One reason is you do not really require a low temperature heat exchanger. Okay. And the fourth reason is main compressor of the aircraft itself can be used for compression. Okay. A typical aircraft engine already has a compressor. Okay. So, you also need a compressor for the air conditioning system. Okay. So, if you are using air cycle refrigeration for air conditioning, you can use the main compressor of the engine itself for compression of the air. Okay. You do not require a separate compressor. So, you can see that you do not require a low temperature heat exchanger, and you also do not require a separate compressor. So, this will lead to significant reduction in the weight. Okay. So, you will find that weight per kilowatt of an air cycle system will be much lower than a comparable vapor compression system, for example, using a reciprocating compressor. In fact, the calculations show that the weight will be typically 50% that of the comparable vapor compression refrigerant systems. Okay. So, this is the these are the reasons why we use air cycle refrigerant systems in aircraft. Of course, the last reason is that this the design of these systems are considerably simpler, and the maintenance is also easy. Okay. So, these are the reasons why we prefer air cycle systems in aircraft. Now there are different types of systems used in different situations and for different types of aircrafts. Okay, for example, you can have what is known as a simple system, you can have a bootstrap system, you can have regenerative system, you can also have what is known as a reduced temperature system. Okay, there are other systems also. Okay, these are the three main systems. The fourth one, as I said, is reduced ambient system. Okay, so each one has its own advantages and disadvantages and applications. Okay, let us quickly look at these systems. The first one is what is known as simple aircraft refrigerant system or a simple system. This is an open system. The power, okay, let me first explain the cycle. Okay. So let me begin at point 2. Okay, and let us look at the TS diagram first. Okay, so this point 1 is the ambient air. Okay, so ambient air, the pressure and temperature of the ambient air are increased due to ram effect. Okay, process 1 to 2 is what is known as the ramming process. Okay, during the ramming process, its pressure and temperature increases. Okay, so what we have basically at point 2 is ram air. Okay, so ram air goes to the main compressor. Okay, MC is the main compressor of your aircraft engine, right? So it goes to the main compressor, it gets compressed from process 2 to 3. Okay, so a part of the compressed air goes to your engine and a part of it goes to the air conditioning system. Okay, so at point 3, the air that is used for air conditioning system enters into an air cooler, AC. Okay, AC is the air cooler. And how do we cool this air here? We again use the ram air for cooling this air. You can see that temperature at point 3 is much higher than the temperature at point 2. So you can use the ram air for cooling this air. Okay, so the process 3-4 is what occurs in the after cooler. The temperature decreases almost isobarically from 3 to 4. Okay, and ram air is used for cooling this. And at this point, at point 4, it enters into the cooling turbine T. Okay, and it undergoes expansion process 4 to 5. And as you know, at this point, you have a very cold air. Okay, at point 5. So cold air at point 5 is released into the cabin directly. So okay, so this air goes to the cabin, and in the cabin it picks up heat, and by the time it comes out of the cabin, its condition will be at point I. Okay, so process 5 to I is what has happened in the cabin, right? And the power output of the turbine here is not used for running the compressor or anything. It is used for running a fan. Okay, so what does this fan do? This fan drives the air through the after cooler. Okay, so that means the power output of the turbine is used for running the fan, and the fan makes sure that sufficient air flows through the air cooler continuously. Okay, so this is what is known as simple system, and here you can see that I have shown the actual cycle. So you have some pressure drops here and non-isentropic processes also. So what is the refrigeration capacity of this system? Refrigeration capacity of this system is nothing but m dot Cp into Ti minus T5, where Ti is the cabin temperature. Okay. Now let me explain the ram effect. Ram effect is the pressure and temperature of the outside air increases as it comes in contact with the aircraft due to the conversion of kinetic energy into enthalpy. See, air may be still, but the aircraft will be moving at very high speed, so there will be large relative velocity between the air and the aircraft. Okay, so when the air comes in contact with the high relative velocity air comes in contact with the aircraft, its kinetic energy will be converted into enthalpy. Okay, so the ultimately you have the enthalpy being converted into temperature and pressure. Okay, so you have, because during this process the kinetic energy is converted finally into pressure and temperature. Okay, so this process is known as ram process or ram effect. Okay, and you can very easily show that the temperature rise during ram effect is given by this relation. Okay, T2 dash by T1. T2 dash is the temperature at the exit of the ram process, T1 is the temperature of the ambient. Okay, this is equal to 1 plus gamma minus 1 by 2 into m square. Okay, where m is nothing but a Mach number. Okay, if you remember, the Mach number is defined as the ratio of the velocity of the aircraft divided by the sonic velocity. So, A is the sonic velocity, right, and sonic velocity, as you know, is for an ideal gas is equal to square root of gamma into R into T1, okay. And the ram efficiency, because the ram process is not strictly isentropic, you can define a ram efficiency as the actual pressure rise, this is the actual pressure rise, and the pressure rise if the process is isentropic. Okay, so we have the ram temperature rise during the ramming and the pressure rise during the ram process. Okay. So, as you can see that the power output of the cooling turbine is used for running the fan, and this system is suitable for ground cooling. Why is it suitable for ground cooling? Because on the ground you do not have the ram effect, okay. Because of the ram effect, always there will be airflow on the air cooler as long as it is moving, but on the ground the aircraft is grounded. So, but still the fan can drive the air, okay. So, this system is generally suitable for ground cooling, and this system is suitable for low speed, low altitude aircraft, okay. So, simple systems are used for low speed and low altitude aircraft. The second system is what is known as the bootstrap system. Let me very quickly explain the bootstrap system. In the bootstrap system, we have two heat exchangers and an auxiliary compressor. So, the ram air gets compressed in the main compressor MC, and at this point it enters into the air cooler. So, point 3 to 4 temperature reduces, and at point 4 again it is compressed in an auxiliary compressor from point 4 to 5, okay. So, the point 4 to 5 is what happens in a auxiliary compressor, okay, and at point 5 again it gets cooled as it flows through the air cooler 2, okay. So, during this process again the temperature drops from 5 to 6, and at this point it enters into the turbine and it undergoes the expansion, and at this point it goes to the cabin. Okay, so you can see the difference between the simple system and the bootstrap system, okay, and here the power output of the turbine is used for running the compressor, right, and the ram air is used for cooling the air cooler 1 and air cooler 2, because the same ram air is used, right. So, obviously you can see that this system is not really good for ground cooling, because when it is on ground you do not have any ram air, so the air coolers cannot be cooled. So, normally you do not use this system for ground cooling, you normally use it for high speed, high altitude flights. So, as I said, suitable for high speed aircraft flying at high altitude, it uses two compressors, two heat exchangers, and not suitable for ground cooling. The other system is what is known as regenerative system. I will not explain this system, but I will just tell the briefly. In a regenerative system, a part of the cold air from cooling turbine is used for pre-cooling the air entering the turbine. That means what is done is you take some cold air from the cooling turbine and use the same cold air for pre-cooling the air, okay. So, that means the air entering into the turbine will be pre-cooled, okay. So, the advantage of this is that exit temperature of the turbine will be very cold, okay. So, in a typical regenerative system you can get very cold air, okay. Of course, this is at the cost of increased weight and design complexity. And one last thing is all the different aircraft cooling systems are compared based on an index called dry air rated temperature, or DART, okay. DART stands for dry air rated temperature. It is defined as the temperature of air at the exit of the cooling turbine in the absence of any moisture condensation, okay. That means when the air is very dry and as it undergoes expansion, there should not be any moisture condensation, okay. Under such cases, what is the temperature at the exit of the turbine? That is called as dry air rated temperature, okay, and this is the index used for comparing different systems. And normally the aircraft systems are rated based on the mass flow rate of air, okay. So, the rating is done based on the mass flow rate of air, and the refrigeration capacity is obviously given by a mass flow rate of air m dot into Cp into Ti minus DART, design DART, that means design dry air rated temperature, and Ti is the cabin temperature, and m dot is the mass flow rate of the air, okay. And a comparison of different aircraft refrigerant systems based on DART at different Mach number shows that DART increases monotonically for all systems except reduced ambient system, and simple system is good at low Mach numbers, and at high Mach numbers we have to use either bootstrap system or regenerative system, and the reduced ambient system is generally good for supersonic aircraft. Okay, let me quickly conclude what we have learned in this particular lecture. We have discussed the reverse Carnot cycle and its limitations, and we have discussed ideal and actual reverse Brayton cycles, and we have looked at various aircraft refrigerant cycles, and we have also seen the concept of dry air rated temperature. And as I mentioned, the performance of all the above systems can be obtained very easily using the basic thermodynamic concepts which we have discussed in the earlier lessons and also in this particular lesson. Okay, right, thank you.